Hey everybody, welcome to chapter 10. So here we're going to be talking about different types of forces that we see in our molecules. Then we're going to be talking about um, different things that come with liquids and solids, right? We just went over gases as an entire chapter. Here we're going to combine liquids and solids themselves. So let's get started. And first off, we're going to talk about intermolecular forces. So intermolecular forces are anytime we have forces that are in between molecules. So think about interstates. They are right highways that run between multiple states. Intermolecular forces are forces that are between multiple molecules, right? And so most of these are going to be between molecular substances, remembering that those are substances that are made up of a bunch of nonmetals, just like nonmetals, right? They are bad conductors of electricity. These are usually things that don't dissolve very well in water, so we call them insoluble in water, but they are soluble in nonpolar solvents because molecular substances are nonpolar themselves, right? And so they also have low melting points, meaning that they are really kind of easy to break apart and to have them turn from a solid into a liquid. But a lot of these a lot of these properties are dealing with the different types of intermolecular forces that are out there. So let's take a look at the different types of intermolecular forces that we might run across. So the three different types of intermolecular forces are dispersion forces, dipole forces, and hydrogen bonding. Dispersion forces are in every substance that you come across. So if I ask you what types of forces are present, then make sure that you include dispersion forces as one of them. Now you might come across these being called London dispersion forces or van der Waals forces. Okay, so if you come across those, these mean the exact same thing. All right, so as the molar mass of something increases, the dispersion forces become stronger. So dispersion forces are just these forces that are because of the movement of electrons in a molecule. So remember that as you've got a molecule, electrons are free to move anywhere throughout that molecule. Now, yeah, we show them as being like localized, where we've got these lone pairs or we've got these bonds, but really electrons can move anywhere they want to. Right, but so as the electrons kind of move around, sometimes they might be all on one side, or they might end up being all on the other side. And because of that, they are going to have attraction between other molecules there. So as the molar mass of something increases, the number of electrons increases as well. And so as you get more and more electrons, as they kind of traverse around, if they're all on one side of the molecule, then they're going to have more of an effect on the molecule that's next to them. And so there's going to be a little bit of a stronger interaction. All right, next off, right, when we've got molecules with a permanent dipole, they display dipole forces. Okay, so when we've got a permanent dipole, remember that was when basically we had that electronegativity difference, right? That was, let's just write it as greater than 0.4. Okay, when you got something like this, right, then you've got adjacent molecules are going to line up so that you've got the negative of one is going to align up with the positive side of another one. Okay, so let's think about that. We could have something like, say, carbon dioxide, or let's say carbon monoxide. Okay, so what's going to happen there is that they are going to align, right, in opposite ways from each other, right, because of the charges that are going to be present there. Because like this side of this is going to be partially negative, and this side of this is going to be partially positive. So it's going to align with the partially negative of the next one, and those are going to align, right? So the negatives and the positives are going to align with each other. And that's going to be a little bit stronger of a force. All right, and then lastly, we have hydrogen bonding, and hydrogen bonding is a very strong type of dipole binding, and it is when you've got a hydrogen directly attached to either a nitrogen, an oxygen, or a fluorine. Okay, so as forces go, dispersion are the weakest, then dipole, then hydrogen bonding. All right, and hydrogen bonding accounts for things like water, and water being really difficult to boil, right? And remember why it has, like, a really high specific heat, right? That's because of the hydrogen bonding there. It's really hard to break those water molecules apart from each other, right? If you got a liquid, it's really hard to heat it up, and it's really hard to turn it into the gas phase because that hydrogen bonding, those water molecules are stuck together really tight. Okay, so let's look at the effect of molar mass on the boiling point of something. Okay, so I've got some different things here. I've got noble gases, halogens, and hydrocarbons here. Okay, but notice that as the molar mass increases, right, the boiling point also increases. So what that's telling us is that as the molar mass increases, right, dispersion forces increase as well. You have stronger forces holding them together, so it's harder to boil whatever the substance is. All right, next up, let's look at the effects of polarity on boiling point. Okay, so at the top there, right, I've got something like nitrogen versus carbon monoxide. So nitrogen, right, has an electronegativity difference of 0, so it's completely nonpolar. Whereas carbon monoxide has like a little bit of an electronegativity difference. All right, now notice that they have basically the exact same molar masses. All right, but there's a little bit of a difference in the boiling point. Right, the carbon monoxide has a slightly higher boiling point. Not a big difference, but a slightly higher boiling point. All right, but as we go down, right, let's look at something like our bromine versus our ICL again, right? So bromine is completely nonpolar, whereas ICL is a little bit polar. And so notice these differences between these boiling points, right? The molar masses are basically the same, and yet there's a relatively big difference in those boiling points there, right? And so the more polar, or the stronger the dipole force, the higher the boiling point is going to be, right? Because again, the stronger the force, the harder it is to rip those molecules apart from each other and turn them into the gas phase, right? Liquid phases are stuck together, hard to break them apart into the gas phase there. All right. Next up, let's just kind of talk about the difference between breaking a covalent bond versus breaking intermolecular forces. So again, we've got our 3 different types of intermolecular forces there. And all of our intermolecular forces are relatively weak compared to the strength of a covalent bond itself. All right, so it's got the attractive energy in ice is about 50 kilojoules per mole, versus the covalent bond in water is about 928 kilojoules per mole. So what this is to separate A water molecule takes about 50 kilojoules per mole. To break the bonds in a water molecule is way more than that. Okay, and so the bonds are much stronger. Bonding is really strong. Okay, so this explains why, when you say take some water and you boil it, right? When you boil water, you're taking the water molecule in the liquid phase and you're turning it into a water vapor, right? But the water molecule stays the same. As you heat it up, it's not like you're separating it into hydrogens and oxygens. You're not breaking bonds, right? The water molecule stays the same, it just changes phases that are in there, right? Even a hydrogen bond, which is the strongest of all of them, right? And that's what's happening between water molecules, right? Well, even that is easier to break apart than to break the water molecules apart themselves. So why are hydrogen bonds so strong? Well, you've got an oxygen, right, in the water molecule here, and the oxygen is pulling electrons towards it. So it is really negatively charged. And then that makes these hydrogens kind of partially positively charged. And hydrogens are really tiny, right? They're number one on the periodic table. They're the smallest elements that are out there. And so water molecules align themselves, and the next hydrogen will kind of tuck itself up next to that oxygen there, right? And again, it's positively charged, and they're really close together, and there's a pretty good disparity in charges there. And so it's really kind of sticking together. So it's not exactly like an ionic bond, but yet there is that kind of attractive force between negative and positive charges. And remember, when you had ionic bonds, the stronger they were because of like the sizes. Well, hydrogen's really small, so it can tuck in there really tightly. All right, let's look at phase transitions. All right, so first off, let's talk about vaporization. All right, vaporization is where you have a liquid and it is converted into the gas phase, right? So a liquid into a gas is called vaporization. The reverse of that is called condensation, right? You might have seen this on like a glass on a warm day where, you got some ice water on the outside of the glass, you get condensation. That's where gas is converted into the liquid phase. All right, next up we have melting. Melting is you're taking a solid and converting it into a liquid. The reverse of that is called freezing. Sometimes we call it solidification or solidifying, but usually it's called freezing. That's where a liquid is converted into a solid. And then lastly, right, one that doesn't happen quite as often but can occur is sublimation. Sublimation is where you take a solid and it goes directly into the gas phase. So it doesn't even go into the liquid phase first. It goes directly from a solid, right? The most famous example of this is probably, right, dry ice does this. It sublimates into the gas phase. And then the reverse of that is something that we call deposition, where gas is converted directly into a solid. All right, next up, we're going to talk quickly about boiling points and what affects our boiling points. So when the vapor pressure of a liquid increases enough to equal the external atmospheric pressure, the liquid reaches its boiling point. Okay, so if you took water, if you've got water at room temperature, there is a vapor pressure that is associated with it. So there is a pressure of the liquid water has some molecules that are kind of hopping up into the vapor phase a little bit. And so there's some sort of a pressure that's going up there, and that's called the vapor pressure. All right, and around room temperature, it's something like, say about 23 millimeters of mercury. Okay, but if you're sitting there at, sea level, you have atmospheric pressure pushing down on it of about 760 millimeters of mercury. Okay, well, as you start increasing the temperature, right, if you put this on a hot plate, right, and you start to increase the temperature of this, and as the temperature goes up, the vapor pressure goes up. And so if you increase the temperature a little bit, maybe your vapor pressure goes up to like 50 millimeters of mercury. All right, well, then once you reach once you reach 100 degrees Celsius, the vapor pressure is 760 millimeters of mercury. You have reached a point where the pressure going up equals the pressure going down on the liquid. And at that point, boiling happens. So, this then depends upon the pressure that is being exerted down upon it. So here in Colorado, right, where we're way above sea level, there is less atmosphere up above us, and so there's less pressure being pushed down upon the water. And so since there's less pressure being pushed down upon the water, then it's easier to boil the water because we don't have to push it to quite as high of a temperature. The normal boiling point of our water, of liquid, is the temperature at which it boils at 1 atmosphere. Right, which is at sea level. That's what we call, by the definition, as the normal boiling point. All right, during the boiling process, it's interesting to note that the temperature remains constant. So as you boil something, it doesn't matter how much heat you keep putting into it. All that heat is going into boiling the water, and so you're not going to change the temperature of it at all. Okay, now if you want to determine the temperature at which something then boils, right, at, say, in Colorado Springs versus, say, at sea level, we can do that by something called the Clausius-Clapeyron equation. Okay, here is the Clausius-Clapeyron equation. It is shown as the natural log of pressure 2 over pressure 1 is equal to the enthalpy of vaporization over R times 1 over T1 minus 1 over T2. This is probably the most complicated looking equation that we get in all of Chem 1. It's all about taking our time to work out everything step by step and doing it really slowly, not getting lost throughout the process. Okay, number one is it doesn't matter what you call pressure 1 and pressure 2 so long as you relate it properly to temperature 1 and temperature 2. It'll still work out mathematically, even if you reverse them all, like as long as whatever temperature goes with the correct pressure and you plug them in properly. All right, your temperatures do have to be in Kelvin. Don't forget to make that conversion or else it's going to be incorrect. The R for this, the gas constant for this, is 8.31 joules per mole Kelvin, right? Or 0.00831 kilojoules per mole Kelvin if our enthalpy of vaporization is in kilojoules. All right, so it says if that has to work for, or enthalpy of vaporization has to be in joules for that R to work. If the enthalpy of vaporization is in kilojoules, you could use the other R. Okay, so here we are in Colorado Springs. Okay, at what temperature does water boil here in Colorado Springs? All right, let's solve for that. So, right, we are at about 6,035 feet above sea level, and we have a atmospheric pressure usually around 603 millimeters of mercury. Okay, so what we want to do is we're going to use our Clausius-Clapeyron equation. We have the natural log of P2 over P1 is equal to the enthalpy of vaporization over R times 1 over T1 minus 1 over T2. So I'm going to say we have 603 millimeters of mercury divided by 760 is equal to 0.793 atmospheres, right? And then the normal boiling point is at 1 atmosphere. All right, now then, we can kind of start plugging things in to see how this works out. Okay, so I'm going to call this P2. So I've got the natural log of P2, which is 0.793 divided by 1. That's our one at sea level, right? Is equal to the enthalpy of vaporization that's given to us is 40.7 kilojoules per mole. All right, and so we're going to use the 0.00831, right, kilojoules per mole Kelvin. All right, now, 1 over T1. Since we called pressure 1 atmosphere, all right, then water boils at 1 atmosphere, all right, at 373 Kelvin. Remember, that is 100 degrees Celsius. Minus 1 over T2. Okay, now we're going to work things out. So you're going to do the natural log of 0.793 divided by 1. So that's going to be negative 0.232. All right, that is equal to, all right, 40.7 divided by our 0.00831 is 4898 times, all right, I've got 1 over 373 is 0.00268 minus 1 over T2. Okay, so next off, right, I'm going to move that over to that side by dividing through. So I get negative 4.74 times 10 to the minus 5th is equal to 0.00268 minus 1 over T2. Right, and now I'm going to move that over to the other side by subtracting it over there. Negative 2.73 times 10 to the minus 3rd, right? Lots of algebra skills here. Is equal to negative 1 over T2. So both sides can become positive, right? I'm going to take the inverse of both sides. And that gives me then T2 is equal to 1 over 2.73 times 10 to the minus 3rd, which is 366.5 Kelvin, minus 273. All right, so water would boil on a normal day here in Colorado Springs at 93.5 degrees Celsius. All right, so that's using the Clausius-Clapeyron equation. All right, the last topic in our chapter here is all about phase diagrams. So phase diagrams are a graphical representation of where we have temperature and pressure and looking at when we have different phases of a material. Okay, so there's 3 things to consider when we look at a phase diagram. And those 3 things to consider are, if you're in a region, then only one phase exists. If you are on a line, then you have two phases existing. All right, so if you're in a region, like right here, right, you're only a solid is existing. If you say we're on a line, like right there, right, on a line in a region, then there's two phases. So right there, we'd be right in between, like, so we'd be in equilibrium between a solid and a gas. And then at a point, there's only one point here, there are three phases existing in equilibria, the solid, liquid, and the gas there. This is called the triple point, by the way. So, right, lost it on the previous slide, so I'm going to draw it real quick here, because for some reason it won't let me go back. It does not like that whatsoever. So solid, liquid, and the gas phase here. So all that was showing is that, right, this is melting, right, this is freezing, right, as I might ask you questions like this. This is vaporization, that way is condensation, sublimation, and deposition. All right, that's all we really kind of missed on that previous slide there as it jumped ahead. All right, now if we refer to our figure here, right, it just wants us to state what phase or phases is present at certain things. I'm just going to do the first one here. There's a couple more, but I'm going to skip them there. If we were at 1 atmosphere and 100 degrees Celsius, so I just want us to point out, so at 1 atmosphere, that is also 760 millimeters of mercury, and 100 degrees Celsius, right, I would be right there. Right, what phase or phases would be present? Well, we're on a line. So both liquid and vapor would be present. I guess I'll do one more here. What if we were at a half an atmosphere? Hard to read through there, but it says a half an atmosphere and 100 degrees Celsius. So a half an atmosphere would be somewhere, right, halfway between like 5, which is about 0, and our 760. So about here and that. So the only thing there, right, we would be in a region. So the only thing there would be, we would be in the vapor phase. All right. So finally, for the melting point of something, right, if you've got a pure substance, both the melting point and the freezing point should be identical, right? So if you've got pure water, right, it melts at 0 degrees Celsius, right? Well, it also freezes at 0 degrees Celsius, right? And when you've got a pure substance, so if you think about going between a liquid and a solid, right, they're pretty condensed already, so pressure really doesn't affect the freezing point and melting point very much. All right, but if you do increase the pressure, it does favor the more dense phase slightly. And most things, right, the solid is usually more dense. Which I think, oh, it does say that. Okay, the solid is usually more dense, right? But there's one really big exception to this. And that really big exception to this is water, right? Because liquid water is more dense than solid water, which is why, like, ice cubes float to the top, right? Because they're less dense than the liquid water that they're in. And so when a solid is denser, then you will get what we call a positive slope of something. All right, and so when we have a positive slope, right, I'm going to exaggerate it on here, but this, the top one here, this is a positive slope. right? That slope kind of angles that direction there, right? This one here is the negative slope, right? That is where the liquid is denser than the solid, right? So that one's where we've got our water, right? There's a few other substances that are out there, but for our purposes, that's where we've got water. Right, so it might pop up on something that you stumble across, but if you see that there's some different slopes in there, that is why. It's because there is a slight change in that effect because of the pressure, and it really does depend upon whether the solid or the liquid is the denser of the two. All right, another chapter down. We'll see you for our final chapter next time.